So, good evening and welcome to this problem solving session or the control engineering course. So, in today's session, we'll discuss about compensator design problem using root locus. So, today's content will be based on the lecture videos of week 8, that is, these are the compensator design using root locus method. So, first of all, why we need some compensator. So this there will be some I will give a very quick recap of this content of week lecture, uh, week 8 lecture video, and then we will solve some basic problem. So the first question will be why we need some compensator. So there usually we have a plant, and we want that plant to satisfy some kind of tangent specification as well as steady state error specification. So the tangent specifications are given, assuming some dominant pole assumption. So we assume that our system has some dominant closed loop poles, so that actually dominate the tangent response, and we had a underdamped systems using these dominant poles. Okay, so for this the tangent response will be the tangent case arises whenever we give a sudden change in the control signal, the input signal. So it will just change from initial state to, and it will achieve the steady state. So before achieving the steady state, the response is called tangent response, as we already know. And this for a second order system, we have a lot of specification that actually define this tangent response, out of which we need some important specifications are the maximum overshoot as well as the steady state, the settling time. So we need our tangent response to die as quickly as possible and reach this steady state. So we need that settling time to be as small as possible. And similarly, we don't want our tangent response to overshoot so much. So we want our maximum overshoot to be limited by some value. So these two specifications fairly defined the dominant closed loop pole location. So it is possible that our plant may not satisfy this requirement. So instead of modifying that plant, which may be costly or it may be impossible to in some situations to modify the plant, we actually use an compensator in cascade with the plant. So this compensator idea will be that using that cascade transfer function, that is the compensator in the plant, will achieve our desired transient response. So as we see that to obtain the desired transient response, your dominant poles location are already fixed by the basic requirement of limited maximum overshoot or some minimum settling time. And this location, it is possible that by some fairly gain adjustment we can achieve that if the location of the poles are located on the root locus. If not, then they should be located in the left hand side, because that is how your transient response actually becomes better and better as you move to the left side of your this S domain plane. So we already know that adding a zero has the effect of pulling that root locus to the left. So we see that one way to achieve that desired transient response will be to add a zero, so that the root locus is pulled to the left, and this root locus lies on the the desired location of the dominant poles. And but we see that realizing that zero is a uncasual system and its realization is possible, so we have to add another pole to the system. So we add a pole and zero combination, but we need that dominance of the zero, that is the angle contribution of the zero of the total compensator should be positive. So we need the pole to be located left to the zero. So now this difference of the angle contribution between the zero and the pole will be the total angle contribution that is given by the compensator, and this is positive. So because the zero is located to the right of the pole, so it is called a lead compensator. And we have multiple option of placing that zero in pole. So we choose somehow we choose this pole and zero, so that we also achieve other criteria. So this criteria are we want our gain of the at the high frequency to be very low, and also a convenient gain value that will put that dominance pole location on the root locus. And also we want the steady state error to be better there. So if we cannot achieve this desired steady state error using only this lead compensator, then we look for lag compensator. So as we already know that the steady state error will depend on the type of the system, that is the location of the pole at the origin, and but we cannot place the pole directly at the origin. So because it will for some gain value it may cause instability, and also it is possible that this for this pole location we may not have this dominant effect of this this pole other dominant the closed loop poles. Okay, so for that we also want to plate in 0, so that we have a near about this pole, so this pole 0 cancellation can occur. But now we see that we should place this pole right of this 0, so that it will have this dominant effect. So the angle contribution, the total angle contribution of this capacitor will be negative, because this pole is located near to the origin and this 0 is located uh, right to this pole for this compensator, and thus it is called a lag compensator. Okay, so if we want both transient and steady state specification to be met, and then we can design these two compensators separately and then cascade. So during this cascade we have to also take care of that this loading effect does not occur. Okay, so using this idea, so we'll solve some basic problems on this compensator design. Okay, so we'll start with lead compensator. Okay, so this problem one, so here we have a model. So we have a plant, so this plant transfer function is fixed, that is given by here. So we want to design this controller so that we meet some specification. This specification are directly given in terms of damping factor and this omega n, that is the natural frequency. And so first question will be where this dominant pole should be located to obtain this kind of specification. So this specification could have been given in terms of also the maximum overshoot and the settling time, and from this maximum overshoot we can compute this damping factor and the settling time, because we have zeta omega n. So if already the damping factor is known, then we can find this omega n. So these two terms, that is the damping factor zeta and this natural frequency omega n, can always be determined depending on our transient response specification. So once this specification is known, then we know where this dominant pole should be located. Okay, so for this second order underdamped system, we know this pole location will be at this point, that is the minus zeta omega n, and this complex part will be omega n square root 1 minus zeta square root of this. So this will give this dominant pole location. So using this given data, we can easily now compute this dominant pole location. So so zeta omega n, so it's 6 into 0.8, so 0.48. So we have this equal to minus 0.48 plus minus, and this is 0.8 times square root of 1 minus 0.6 square. So we have 0.64. Okay, 0.64. So these are the location of the dominant poles. Okay, so we have this complex conjugate poles because we want to be underdamped system. So these specifications are valid for only second order underdamped system. So we want this. So we see that the option will be this one. So the dominant poles are located at this point. So once we have this dominant pole location, now we want to verify whether a simple gain adjustment can actually by through a simple gain adjustment can we have this dominant pole location over this root locus. And so the idea will be how to verify this will be whether this angle contribution, that is the all these open loop poles and 0 to this dominant pole location, if it is minus 180 degree, then we know that there is some gain for which we can place this dominant poles over the root locus, right? So if this angle is not minus 180 degree, then definitely using a simple gain adjustment we cannot have this dominant poles over this root locus. Okay, so first we determine whether this pole location this actually lies on the root locus. Okay, so to see this we have to find this angle contribution, that is for this Okay, so now we ignore this controller, so it should be like some gain only, just proportional controller. And for that we see whether we can have this dominant pole location over this root locus. So for that, let's just plot it in the S domain for clarity. So our pole locations are 0.48 plus minus this. So this is let minus 0.48, and this is 0.64. Okay, so this is the j omega axis, and this is minus 0.64. So this dominant pole should be located at this point. Okay, now for this transfer function, there is no 0, but this open loop transfer function, we have two poles at the origin and minus 0.5. So one is located at this minus 0.5 and one located at the origin 0. So this angle contribution will be what then to this dominant pole? For one pole it's enough to compute this is one angle, so let it be theta 1, and another angle, this is theta 2. Okay, so to compute this, so we simply can compute, because this angle we can compute, and this angle is just 180 degree minus this angle, so we can just use the tan inverse to compute this angle. And similarly this angle, this again using the tan inverse formula, we can compute this angle also. Okay, so let's compute this two angle. So first, because this is minus 0.5, so this length will be 0.02, and this height is 0.06. okay, so then so first we compute this theta 2. So theta 2 will be what? Tan inverse of this height by this base. Okay, so it's 0.64 this height here, and this base height is 0.02, and theta 1 will be then so tan inverse of, so this is theta 1, so 180 degree in this angle we compute first, then we just subtract from 180 degree. So directly write this, so it will be 180 degree minus tan inverse, so this height is again 0.64 and this base is 0.48. okay, so this angle theta 2 is just compute. So using that calculator directly compute this, so it is 0.64 by 0.02, so it's 88.21. okay, so this this is how we compute this angles. Okay, so and this angle is 180 degree minus, again using that tan inverse formula, it is 48, so it is 180 degree minus this angle, so it is 53.13, so it's equal to 126. degree. So this is this two angle. So then the total angle that is contributed by this plant, okay, only will be just this addition of these two angle. Do you see that this is this plant contribution angle at this HD. This is the dominant pole will be this two angle addition. So it's approximately 215.08 degree. Okay, so we see that this dominant pole actually does not lie on this root locus, right? Because this angle contribution should be minus 180 degree, but it's not. And we see that then what should be the angle contribution for by this controller will be this angle deficiency, that is the other angle should be provided by this controller such that this total angle become 180 degree. And we will see that this angle deficiency will always be positive because we want to meet this transient specification, then we require a lead compensator, so this angle will be positive contribution. So but we need what, then we need this contribution by this controller plus this plant should be minus 180 degree. So this contribution then by this will be then so minus 180 degree. So again this is negative because of the pole, right? So let's just correct this. So this is negative of this negative. Okay, so this minus, because these are poles, so this angle contribution will be negative because these two angles. Okay, so then we get, yeah, okay, so 215.08, so it's approximately equal to 35. Okay, 35.08 degree. So is that D? Okay, so to just recapitulate, so what we did is that we first observed that what is this angle contribution from this plant only, okay, at this dominant pole location, and we see that this angle is not 180 degree, minus 180 degree, or the odd multiple of minus 180 degree. So that means that this dominant poles are not located on the root locus. So by simple gain adjustment we cannot place this pole to be at the this dominant pole locations, that is the desired one, that should achieve our the transient response. And we see that what angle that has to be given, that is the deficiency of the angle that has to be contributed by this compensator, so that this dominant poles are located on the root locus. So this angle is just we calculate by simply using this formula, that is this total angle contribution by this compensator and this plant will be minus 180 degree. So then we can easily compute this angle contribution that this compensator should give. So that is this angle deficiency, and that is just we found 35 degree. Okay, so now we can design our compensator that will give this angle contribution, so that this dominant poles will be located on the root locus. Okay, so the next question will be like how to find this location of this ZC and PC, that is the location of this compensator 0 and pole. Okay, so again, as you know, there are many possible way to locate them, but to optimally locate we already know how to find this formula. So we first compute this gamma, which is defined by pi or 180 degree. So 180 degree minus theta minus this phi. So where theta is simply this cos inverse zeta, okay, and phi is this angle deficiency. So angle deficiency we already have 35 degree. Okay. So and this cos inverse zeta is given 0.6, so we can find cos inverse of this. So we have cos inverse of 0.6 is this is cos inverse of 0.6, and this is 53.13 degree. Okay, so then using that, gamma is simply half 180 degree minus theta is 53.13 degree minus 35. So it's computed. So 180 degree minus 53.13 minus 35 by 2, so it is 45.9 this is 40.9 degree. Okay, so this is the gamma angle degree. So then we find this location of the 0 and 4. Okay, so for this compensator. So again, okay, so you can use direct formula to compute that. So this formula I'll write here. Using the direct formula, you always compute this 0 and 4 location, and if you don't remember, you can also like graphically compute them. So this direct formula, the location of this 0, so these are mentioned in the lecture video. So this is sine gamma by sine gamma plus theta, and this location of the pole will be this sine gamma plus theta plus phi. Okay. So using that you can directly find. Otherwise, if you don't remember this formula, then you can easily compute from the graph also, like this pole 0 diagram. So okay, so you want your dominant pole to be located here, so it is minus 0.48 and it is j 0.64. okay, now you want to place, okay, so let you want to place pole here and the 0 of the compensator here, then we know that this angle should be gamma from that pole. This is the location of the PC and this is the ZC, and this angle should be then phi plus gamma. So you see that the total contribution will be this angle contributed by this pole, which is phi plus gamma, and this angle that will be subtracted for that pole. So 0 contributed this angle and the pole contributed gamma, so their subtraction will be phi. So the total contribution of this compensator will be then be phi, right? That is what we need. Okay. So using now directly using again 10 formula, 10 we can easily compute this 0 pole location. Okay, so for simplicity, let this is a, this distance from this point minus 0.48 to this ZC, and this minus 0.48 to this PC be B. Okay, this B. So then it is easy to check that this, again this is one triangle. Okay, this triangle, this phi angle then will be what? Tan of phi should be equal to this height by this base. So this height is 0.64 and this base is A. So using that we can find A, so directly. So A equal to then 0.64 by 10 phi. So 10 phi equal to then 0.64 by 10 phi is phi angle. We already computed that. So 35 there. So your 1035. So this is okay. Just compute this. So 0.64 by 10 of 35 degree. Okay, so this is 0.914. okay, similarly we can compute B. So again we have this outer triangle, this one, this green color. So the height will be again 0.64 and the base will be what? This distance B. Okay, so we have this for 10 gamma. So okay, sorry, okay, so this angle, actually sorry, this is phi plus gamma, right? This angle, so 10 phi plus gamma. So you just put 35 plus gamma, we computed 45.9. okay, so I'll just rectify this. Okay, so because this angle, as you can see, let me draw this. So this angle is phi plus gamma. Okay, so this angle phi plus gamma. So okay, let's draw this triangle clearly, so it will be okay. So what we have, this is the location of the dominant pole. So it is located at this point. So it is minus 0.48 and this is 0.64 this is location of the 0 in ZC, and this height, this base length we take A, okay, and this is pole, and this base length from this point 0.48 to this we take B, and this angle is gamma, and this angle is phi plus gamma, okay. So now we consider, okay, this red color triangle. So then we see that 10 phi plus gamma will be this height by A. This is what we have written here. So again, so we just compute this. From this A is unknown, phi and gamma are known, so we can compute A, and this is 35, so 0.64 by 10 of 35 plus 45.9 degree, so it's equal to 0.1025, okay. Similarly, now we consider the outer triangle, so this green one, okay. So this, for green one we have what, 10 gamma equal to, again this height is same 0.64, but this base is B, so we have B equal to then 0.64 by 10 of gamma, and gamma is what we computed it to be 45.9 degree, so it is equal to 0.64 by 10 of 45.9 degree, and its value is 0.6202, okay. So now the location of this 0 and the pole are what? So this is this location, this plus this addition, right? So we see that this is 0.48 and this is this one A, we computed 0.1025, so the addition will be the total location of this 0 to this left of this origin with the negative sign, okay. So this is just we add this 0.48 plus 0.1025, so it is, okay. So 0 location then will be what, the addition of this and 0.48, so it's 0.5825, this pole location, so negative sign because this is located to the left of the origin, and similarly the pole location will be this B plus this magnitude of this 0.48, so it is 0.48 plus B, we have computed this one, so 6202, so it's 1 point minus of 1.1002, so these are the location of the 0 and pole of the compensator, okay. So 0 is 0.5825, pole is this one, so C option is correct, okay. So these are the locations. So and we can easily compute also from this formula. If you know the formula, just substitute and also compute this 0 and pole location, okay. So this will give some positive sign, so you have to take the negative of this because these are located right side of the origin, so you just put negative sign here, so that will mean that this 0 and pole are located to the right side of the left of this origin, okay, in the left hand side of plane, okay. So now, okay, so we already have this transient response specification that are made using this lead compensator. Now we see that what value of the gain will will achieve this dominant pole on the root locus. So we already have this dominant pole on the root locus, but now we need also gain. So from the gain condition you can easily compute the compensator gain, because this plant gain is given here 1, so the total gain should be provided by the compensator. So okay, so we need that this gain of this GC and this plant compensator is denoted by that G, yes. So this magnitude criteria, from that we know that this should be 1, right, if that point has to lie on the root locus. So we just substitute, instead of S we just substitute SD, so SD is the location of this dominant pole, so then that should also equal to 1, then the dominant pole will be located on the root locus, and from this condition we can compute K, because the K is unknown, or the Kc, that is the gain of this compensator, is unknown. We can compute this Kc. So for that value of the compensator, this dominant pole will be located on the root locus. Okay, so that means we just substitute our compensator and this pole transfer function. So the compensator transfer function will be what? So if this 0 and poles are present at this point, then we transfer function is what? Kc s minus Zc by s minus Pc. Okay, so because we have taken Zc in Pc minus and minus, so a negative sign, so we put this the compensator. Okay, so that and this, so this is Kc okay. So this and the transfer function of this plant is given this, so 1 by s plus 5. So okay, this we take sd with dominant pole location, so 1 by sd plus 5.5 0.5. okay, so this magnitude should be 1. So from that we can find this Kc value. So the Kc will be then what? This is just, we just take this all this to other side, so we have sd minus Pc, this sd plus 0.5 by sd minus Zc magnitude. Okay, so just compute all this magnitude. So first we compute this. Okay, so all these terms, okay, because these are all complex numbers, so we just enumerate all this value. So sd is the location of this dominant pole, so it is 0.48 plus okay, we have already computed that pole, 0.48 plus minus J64. okay, so we write that, so plus minus J omega n is 0.64. okay, so we can just take one dominant pole, that's enough, because that magnitude will be same, right, for both complex conjugate plus or minus sign. Okay, so then we have sd plus 0.5 will be then what? So this is minus plus 0.02 plus minus J 0.64 sd minus Pc will be, because this is located this, so we have minus 0.48 plus this is 1.1002. okay, so this is the real part plus point, imaginary part will be same for each cases, and this is minus 4.8 plus 0.5, it is the 0 located this, so 0.5825 plus minus J 0.64. okay, so we just substitute that all in this case, and this magnitude will be what? So we have this real part square plus imaginary part square root. okay, we just put everything there and we compute that. okay, so that's simple computation, and this will result, I will just compute using calculator, so this will result 0.7043. so we can just verify this, just putting this. okay, so then we see that for this gain value of this compensator, lead compensator, this dominant pole will be, now because this is a dominant pole already root locus and the opposite root locus, so for this gain the dominant pole will be located at the desired location of this. okay, so the next question is that okay, so we already have a single lead compensator, but now consider the angle deficiency is very large, then instead of one lead compensator we can use multiple lead compensator. okay, so like two lead compensator, so each one contributing some angle, so in total they both actually contribute to the desired this angle that is required, desired that positive angle that is required, so that we okay, Okay, so in this question we see that okay, so we already know that the lead compensator should provide this positive angle, that is the compensation angle, so that our transient response situation are met. Okay, so it is possible that this angle deficiency will be very large, so this compensator has to provide very high positive angle. So instead of now one lead compensator, we can have multiple lead compensator, like for example two lead compensator. So each of them will be providing some angle contribution, and both angle contribution should add up to the desired angle contribution that this lead compensator should provide. Okay, so we already computed this angle efficiency here. So 35 degree. Okay, so this 35 degree has to provided by one lead compensator. Now we have two lead compensator, and we want this network to be same, that is each should provide half of this angle. So this is by 2. So this is the phi angle first we have computed for the single lead compensator. Now we want each lead compensator, so we have two compensator, each providing the half of this angle. Okay, so we have 35 degree, then half of this is 17.5 degree. So each of the lead compensator should provide this angle. Okay, so then if each are providing that this much of angle, then the location of the zero and pole of the each compensator, so each compensator are like identical, so their zero and pole will be located at the same place. So how to compute that? Okay, so again we use the same formula. So first we compute this gamma. Okay, so we already have this theta angle, so theta is the cos inverse of this theta, so we already computed that here. So this one, theta is 53.13 degree, so we are given here. Okay, so we already have computed theta 53.13 degree, and now each of the lead compensator should provide an angle of 17.5 degree, half of this required angle. So then using this formula we can always compute this gamma. So this gamma is simply half pi minus theta minus phi. Okay, so we see that this gamma will be then, so 180 degree minus this theta is 53.13, and this phi now will be 17.5. Okay, so by 2, so this equal to 54.6 degree. Okay, so this much of angle should each lead compensator should provide now. Okay. So as you can see, earlier when there is single lead compensator, this gamma was found to be here 45.9 degree. Okay, now it's 54.69 degree. Now using this, because we know this gamma, this phi, we can find this pole and zero location of this lead compensator, each of this lead compensator. So again we can use this graphical approach, that is here. So these are this dominant pole location, which are easily found using this damping factor and the natural frequency, right? So we already computed them to be this one. Okay, so this is 0.48 minus, and this is 0.64. Okay, so J. Okay, so this, and now let our zero of this compensator 0 to be here, and this pole, because it's a lead compensator, this pole will be located left of this 0, be this one. Okay, so then we know that this angle contribution should be what? This will be gamma, and this will be phi plus gamma. Okay, so the total angle contribution of this compensator will be then this angle contribution from this 0 minus this pole. So we see that phi plus gamma minus gamma, it's phi again. So this is what we need, angle contribution 17.5. So now we just compute the location of this pole and 0. Okay, again we'll see that we can construct triangle here. This is 90 degree, so let this will be A, this distance. Okay, and this from pole to this location of this point 48 to be B. Okay, then we see that first consider this inner triangle, this red one. So for that we have tan of phi plus gamma should be what? this height by this base, which is height is 0.64 and the base is a. So we can compute this a to be what, 0.64 by 10 phi plus gamma. Okay, now this location of the 0 will be what then? This will be located at this a plus this distance, right? So a plus 0.48, but it's located left to the origin, so it's a negative sign of this. Okay, so this will be the 0 location. So let's compute this term. So first we find this 0.64 by 10 by angle is phi is 17.5 and theta this is sorry gamma is 54.69. So it's okay, a is actually 0.2056. So this ZC location will be then what? This plus 0.48. So it is minus of 0.6856. okay, 7. This is, so this plus this one with negative sign will give this 0 location. Similarly for pole location we will use this outer triangle to compute this b that we have defined this distance from this point 8, right? This, so for this triangle we see that this angle is gamma, so tan of gamma will be height, this is again 0.64 by base is what we have taken it to b. Okay, so again b will be equal to then 0.64 by tan of gamma. So tan of gamma is gamma angle is 54.69 degree, this one. So we have 0.64 by tan of 54.69, so it is 0.4533. So again this to be added to be 0.48 will give the location of this pole, right? This is this location of the pole, so this will be negative sign. So this is 0.4533 plus 0.48, so it will be 0 minus of 333. Okay, this is the location of the pole. Okay, this is that. So this one is the correct answer, right? 6 approximately this one, and this is the 0 location and this is the pole location. Okay, so if you want to just use directly the formula, then you already learned this in lecture video. These are the formula also you can use directly instead of constructing the triangle. That is the formula, because you already know this gamma angle, theta angle and phi angle with negative sign. This will give this location of the 0 and pole. Okay, if you don't want to remember this formula, then you can always construct this triangle and also compute this 0 and pole location of this lead compensator. Okay, so this next problem will be, okay, so we are given some transfer function. Now we want to find, the compensator to be such that this steady state error requirement, that's kV, and this tangent specification should be met. Okay, so then using that, first find this dominance pole. So we first locate this dominance pole location. Okay, so to find that we need, because the dominance pole location is given by this formula, right? For the second order system, omega n minus 1 zeta. So we need both omega n and zeta, that is the damping factor as well as the natural frequency. And using this maximum overshoot, we can always compute this damping factor, so which is by using this formula, I square plus ln square mp. Okay, so this is coming directly from this formula, because this maximum overshoot is given by e power minus pi zeta by 1 minus zeta square. Okay, so from that this formula is coming. Okay, so first we compute this zeta value, that is the damping factor. So again using that calculator, so this is given in percentage, so in a fraction it will be 0.0152. okay, 0.0152 by pi square root of pi square plus ln 0.0152 square. So this is equal to 0.7998. So approximately we can take 0.8. Okay, this is the damping factor we found. Or okay, so or 95 is okay, so approximate value will be something closer to that. Okay, whatever given is come to that. Okay, so then we find this omega n value. Okay, so omega n will be what? Because from this settling time, we know that the settling time will be 4 by zeta omega n. Okay, so and it is given 0.3, and this we already computed to be 0.7998. Then this omega we can easily compute. So 4 by 5.03 into 0.7998. Okay, so it's approximately coming 0.9 omega n equal to 0.994243. Okay, so then this zeta omega n will be what then? Only just we divide this. Okay, so it is 4 by this, right? So again also we can count zeta omega n equal to 4 by 5.03 from this, 4 by settling time. Okay, so 4 by 5.03, so it's 0.795, and so this is this one. The imaginary part will be what? Omega n into 1 minus zeta square. So omega n we have computed 0.9943 into square root of 1 minus 0.7998. So this is this damping factor. So it's this term is 0.59. Okay, 5968. Okay, so I think some error is there, so it should be something 59. Okay, it should be 5. Okay, so this should be the correct answer. Some error is there, 59 something. Okay, 68 or 64. This will be 5, not 4. Okay, this is the location of this dominant pole. So this is just simple formula. You are given damping factor and settling time. You can always find this location of this, this dominant pole, the second order dominant poles. So once you find from the damping factor, you find this zeta damping factor. Then from this maximum overshoot, you find this damping factor zeta, and from the settling time, you can find this zeta omega n. Once this zeta is known, you can find omega n. Once you know zeta and omega n, then this is this location of this dominant pole. So you can just simply substitute and find. Okay. So next, so we want to meet this specification for this system. Now we want to find if a gain adjustment, only through gain adjustment can we have this transient specification, can it be met. Okay, so for this gain adjustment, then what we need, this magnitude of this compensator and this plant at this dominant point should be 1. So this is the magnitude condition, right? If that point lies on the root locus, then that should be the magnitude should be 1. And now from this k, we can just use this k value to find this location of this, this k value to find this location of this, what is this magnitude of the k, that would put this dominant pole in this desired location, right, on this root locus. Okay, now we see that we don't have a compensator here. Instead of that, we just want to find if only by this gain adjustment can we place. Okay, so this k is there, so we take this magnitude, this k by s plus this s plus 4 at this location. So this SD we already computed this one, see, right? So SD we just write this location minus 0.795 plus minus j 0.5964. Okay, this is the location of the desired location of the dominant pole. So I will substitute instead of s this SD, and we want that magnitude to be 1, or you can easily see that k will be just taking this other side. will be this, right? Instead of the S, we want this to be SD, that is dominance for location, SD plus 4. So this magnitude, from this we can compute this K. Okay, so to find that, let's find what are these values of this. So these are all complex number, so we just find this value. So SD already we have this, so SD plus 2 will be what? Then just we add this 2 to the real part, so 2 minus 0.795. Okay, so it will be 1.205 plus minus j. This is imaginary part will be same because only we are adding real terms, right? So similarly SD plus 4 will be what? So we add 4 to this complex number, so it will be 3.205 plus minus j 0.5964. Okay, now we know that magnitude of the complex number will be what? So this is the magnitude of the complex number, the real part square plus imaginary part square, whole square root of it. So we add this and take this, so we can find this magnitude of each number, right? So just compute this using calculator. So first one will be what? Then 0.795 square plus this imaginary square plus real square plus imaginary square, so 0.5964 square. Okay, second term will be this one, so this again real square plus imaginary square, square root of that. Okay, the square root of 1.205 square plus 0.5964 square, and the third term will be again this square plus this square, so real part is 3.205 square and imaginary part will be 0.5964 square and square root of that term. So just substituting that, we find that this gain will be 0.4. So you just use this calculator to find this. So this is the gain. So using this K value, we can achieve this desired transient response, that is the overshoot to be this value and the settling time to be this given value. Okay, so now we see that what is this velocity error constant with this compensated gain. So our requirement is this velocity error, but are we able to achieve this? And if not, then we'll actually use this lag compensator to achieve this this desired velocity error. But first we see that with this uncompensated system, so we have already this gain value. Using that gain value, what will be this kV value, that is the velocity error constant value. Okay, so simply we know that this kV will be what? This limit of s goes to 0 s time gs, right? So we just substitute that limit s goes to 0 and we have s times k, so g this is given here, s plus 2 s plus 4, so this ss will cancel, and when s goes to 0 this will be 2 and this is 4, so k by 2 into 4, so equal to k by 8. Okay, and k we already computed this one, 4.36, so it will be 4.36 by 8, so it is 4.36 by 8, so it is 0.545. Okay, so this is this velocity error we get for this uncompensated system, that is we only varied this gain, right? We varied this gain to achieve this desired transient response, and we see that only this gain variation can achieve this desired transient response, but not this velocity error constant, right? We require this velocity error constant, but what we are observing that we only got this, so this is very less than what we want. So what we will do then, we will actually design a lead compensator that can give this velocity error constant, right? We already have this transient response restriction that are met. Now lag compensator, because we want this velocity error constant to be increased, so we will use a lag compensator. That means we will place one pole near to the origin and 0 left to that. Okay, because only just placing that pole will hinder this dominance effect, and also it will make, as you already know, that adding an pole will make the system unstable because it will pull this root across to the right. Okay, so that's why we need in the lag compensator both an 0 and pole that will very close to each other, so they will cancel in effect, so the angle contribution will be also very less. So this, if the angle contribution is very less from this compensator, then we know that the transient response will not also vary much after adding that lag compensator. Okay, so now we will design this lag compensator. So first we see, so what is this lag compensator? So the lag compensator will have a zero and pole. So let's write this compensator. So let this is the lag compensator. So then this is this beta term, where beta will be greater than 1. Okay, much more than 1. So beta will depend on how much this error constant you want. Okay, so this is, as we see, so this location will be like this. So you have a pole and a 0. So this both will be located very near to the origin. Okay, for this compensator. So let this PC and this JC. So we will find this location. So first we see that what is actually we are obtaining this kV value and what is desired. From that we can find this beta, right? So this is the ratio of that. So this is this kV that is desired. Okay, so I will denote this desired, and this is kV of the uncompensated system. From that we find this beta value. So we see that this is desired is what? This is given 5.45, and for the uncompensated system this is 0.545. So we see that it's 10 value. So this amount of beta we need. Okay, and we, if you remember from the lecture video, so this is just the ratio of this beta is approximately equal to the ratio of this 0 by 4, right? This is approximately this ratio. So from beta we see that once this beta is done, this location of this 0 and pole are arbitrary, right? Because we only need the ratio to be this beta value 10. Okay, so that means, okay, so this location can be arbitrarily chosen depending on this. Once you choose one 0 or pole location, then other location is fixed, right? By this beta. Okay, so we'll see what beta will actually. So we have already beta found, beta equal to 10. So now we want what should be the location of this 0 and pole of this compensator. Okay, so as you can easily see, because I already mentioned that you need this pole and 0 both need to be close to the origin, so that they should be very close to each other, but the ratio should be very high. Okay, that's why we need them to be very close to the origin, because they can be very close to each other, still the ratio should be high. Okay, and this ratio is the beta. So beta is already we computed 10. So then we see that the pole and 0 location will be what? So something, this actually one satisfactory reaction. So there is not like unique solution, but the ratio should be beta, and there should be what? This is the 0 location and this is the pole. Okay, so I'll just cross for pole. So this, because you want the effect of the pole to be dominating, so this should be near to the origin and as compared to the 0, and that's why this angle contribution will be more from this pole than the 0. So we see that this is a lag compensator, because this angle will be, because this is subtracting from this, so a negative angle will be contributed by this compensator, this lag compensator. And also intuitively, because you want to have a better error constant, so your pole should be what? It should be located near to the origin, because you see that your type of the system is determined by the location of the pole at the origin, right? So now we are not placing that pole exactly origin, but very close to the origin, and 0 to the left of this. You see that this location are very close to each other. Okay, this 0 and pole, but their ratio is very high, because they are very small number. The ratio is, you see that beta is 10. So for that we can achieve your desired velocity error constant, but still placing them in very vicinity of the origin, so that for some gain value they will be very close to each other, because your root locus will be like this, right? this is the open loop poles and 0. So as the gain value is increased, you see that your root locus will be moving like this. Okay, so it will be, this pole will be very close to this 0, right, the closed loop poles. So they will in effect cancel each other, and this angle contribution will be very small, because you don't want to disturb this transient specification, right? You already fixed your transient specification. Now you are just adding an lag compensator. So this lag compensator should not also contribute very large angle, right? So that otherwise your root locus will shift and your transition will not be met. That's why you will also need them to be very close to each other, still providing this ratio, that is the ratio should be high. Okay, so this is how you design this lag compensator. So again, just to briefly overview the steps. Okay, so step will be more or less the same. Okay, so I'll just recapitulate the steps. Okay, so what we do, so okay, so you want to meet both transient specification as well as the steady state specification. So this transient specification will be fairly given by some parameter like transient parameter. It will be like maximum overshoot or settling time. So these are the commonly given. So once this maximum overshoot and settling time are given, we can always compute this damping factor and this natural frequency. Okay, by this formula, because your maximum overshoot is related to this zeta and your settling time is related to zeta omega n, right? So once these two are given, the transient specification are given, you can easily find a damping factor as well as the natural frequency omega n. So once these two are obtained, you know the location of the dominant closed loop poles, right? So these are the location for the second order system. So you assume that you have a dominant second order system, then these are the location of the poles to achieve this desired transient specification. Okay, now we verify whether a simple gain adjustment can place this closed loop poles at the desired location. If not, that means if your transient specification are for a given plant are worse, that means you are in the right of this location. Because okay, if you are in the right location of this dominant pole, then your transient specification are bad, right, for this system. If you are left, then you already are meeting this transient specification. So the fact will be that you will be right of this. So you want to pull your root locus. So for example, this type of graph is there, you want to pull this to the left. So you know that adding a 0 will pull this root locus to the left. So to have desired transient response, you add a 0. But adding on simple 0 will be a non-causal system, right? It will be just a numerator term. But you want a causal system, that is you have to have equal number of 0 and pole for this compensator also to design it. So you have to add both 0 and pole, and you see that this pole will be what? So you add a 0 and this pole will be left of this. So this effect of this 0 will be dominant there. So the total angle contribution from both will be positive, because you want to add a positive number. As you can see, positive angle contribution as we already computed here, is it? So a positive angle to be added. So your pole should be left of this 0 there. Okay, so now again the total angle contribution from this pole and 0 should be this one, right? So what we are doing now, you are adding compensator with this 0 and this pole, and this is the dominant pole location. Then you want, this is the contribution from the pole and this is the contribution from 0. So these two difference should be the total angle contribution from this compensator, right? And this was gamma and this gamma, then this angle contribution will be this minus this, so phi. So once you find this phi, then you see that this is the angle efficiency. There is many ways you can place this 0 and pole, right? So this is 0 and pole. Now we want to optimally place them. So to optimally place them, you already seen the lecture video, you have to first find this gamma. Once you find this gamma using this theta and phi, so phi you already this angle efficiency and theta is this angle. Okay, this angle, this is the theta equal to then cos inverse of theta, because this is this theta line, right? Okay, so once you find this, then you find this gamma value. So after this gamma, you can use this direct formula as given in the lecture video, or you can Also construct from the triangle, directly constructing the triangle, you can find the location of the pole and zero of this compensator. Okay, so this is how you design this lead compensator to meet the tangent specification. Okay, so it is possible that now, okay, you already achieve your desired tangent specification. So what about the steady state error? Okay, so it is possible that with this compensator you can achieve whatever you require your steady state error, but it is also possible that your steady state error is very poor. Okay, so that is very small. You want to achieve a high steady state error, as we have seen in the last example here. Okay, so you see that a steady state, this velocity error constant for the steady state error, that is the kV value here, is small as compared to what is desired. Then you go for the lag compensator. So in the lag compensator, what? So the idea is that once you have a pole at the origin, your type of the system will increase, right? As you add a pole at the origin, your type of the system will increase and you will achieve better steady state performance. But you need also know that if you add a pole directly at the origin, it's possible that because adding a pole will pull this root locus to the right? So your system may become unstable for high gain value. Also, your dominance effect will be not be met, right? Because you want your dominant pole, uh, some pole to be located like this dominant pole, and other pole and zero to be located far to the left, right? But if you are adding a pole here, then these are not now dominant pole. You want to cancel them. So how you cancel? You add a zero there. So now instead of adding this pole at the origin, you add somewhere near the origin and then zero left of this. So this will together will contribute this lag compensator, and you want this ratio to be very high because this ratio will actually contribute to your this error constant, right? As you can see, this is divided by this given one. So this ratio will be very high. It should be greater than 1 for this lag compensator, and you want to be exactly what value, that is the divided by this already, what you are achieving for the uncompensated system. So this can be achieved by placing this zero and pole near to the origin, so they will be very close to each other. Still their ratio will be high, the magnitude of this ratio. Okay, so then we have also now liberty of choosing this zero and pole of this compensator. Okay, but again, choosing that, you have to verify whether this angle contribution from them are very small or not. So that can be verified using simulation MATLAB. So you just verify the tangent response, or you just verify the root locus, like plotting that whether your desired pole location are shifted much or not. Okay, so that verification has to be done, so that we are not doing here, but you can do using root locus. Numerical is not possible, like using, in the hand it's not possible, so you have to use just root MATLAB or any numerical software to plot them and verify. Okay, so this is the idea of uh, compensator design in the using that root locus technique. Okay, so any question on this or any regarding this uh, compensator design on the using the root locus, you can ask. Okay, so the steps will be same. Okay, just you have to just use compute them. Okay, so any doubt?